Today I'll be talking about how to build a thriving community, not just a scientific community. I'm kind of coming from a science standpoint and somewhat federal agency standpoint, but I think a lot of these practices transfer to any computing community, and kind of thinking about how we use Jupyter as a process, not just a product. This is kind of coming from the research community that I helped to lead, which is called CryoCloud, and I'll get into that in just a moment. But I want to thank all of our collaborators. A number of different JupyterHub leads and administrators have contributed to some of the data that I'll show you today, and also recognize our funders, and thank you to Jupyter for having us here. So getting started, thinking about science and using Jupyter. In science, we're taking a look at very complex systems. This one is Antarctica, where I work. You have atmospheric researchers who are studying the atmosphere, oceanographers, and glaciologists working in the system. But these are really complex interconnected systems, and a lot of the most exciting questions are sitting at the interface, and a lot of the most unanswered questions are sitting there. So how do we connect researchers or community members to kind of get at these questions that sit at the interface, and that's through interconnected communities. So that's what we're going to be thinking about today, is how to facilitate that. I'm going to talk about advancements enabled by a JupyterHub, trends in user usage and experiences, ongoing barriers for users, and a roadmap for a thriving community that we'll end with. So starting with CryoCloud, I'll give you a little bit of background on our JupyterHub community. It started out as a cryosphere community, but cryosphere researchers, it doesn't just include, glaciologists or one kind of field. It kind of branched out to be a broader community. So this is a number of communities that are a part of this JupyterHub community. Its origin was with NASA and the ISAT-2 satellite mission. ISAT-2 measures the surface elevation of the Earth. And at one of the science team meetings in 2022, a lot of the researchers were complaining about the cloud and needing to transition to it because they were having a lot of problems. So non-intuitive pricing structures, computing options and infrastructure, poor documentation. They were spending a lot more money than they expected to because their IT teams were setting them up in ways that spent a lot of money, and they weren't obviously more collaborative or faster. And myself, I was a postdoc at the time, and Joanna Millstein, who was a graduate student at the time, we'd worked on some 2I2C built JupyterHubs before and knew that this really didn't ring true to our experience. So we decided to work with 2I2C to build a JupyterHub cloud computing platform for our community to use. So we built the platform with bumpers. It's simple and cost-effective managed cloud computing environment for training and transitioning new users to the cloud and determining community best practices. So you can find us at cryonthecloud.com. And we have 850 users now from all parts of geoscience data and tooling chains. We grow organically. We have a number of onboarding workshops, but we accept researchers if they reach out to us who are from geoscience because we have all of our training online and recorded. And we run our JupyterHub in AWS. Some of our achievements are that we've supported 17 hack weeks and workshops over the last 3 years, 17 research publications to date. The CryoCloud team has given 34 open science presentations, written several manuscripts and white papers, and have 2 open science recognition prizes. So that's our background, and now I'm going to get into what we've kind of learned. So why JupyterHub for science, or for any of our communities, obviously? It gives the user a curated experience, right? There's flexibility, modularity, and interoperability. No matter what location, data, or tools you use, it's kind of agnostic to that. So that's really exciting and makes it possible for the seamless support of a number of communities. So this is a few of the scientific communities we work with. Each of these has different kinds of users, deployment structures, guardrails, storage, and compute allowances. What's also exciting is that recently, in the last year or so, it can now support interdisciplinary communities and evolving research projects. So we now have the advent of being able to bring our own images and environments, and not just that, to build our own with the touch of a button. So that means scientists or anyone else using a JupyterHub doesn't need to have software development experience. This means that we can minimize the hub-imposed community boundaries. Our users are no longer just restricted to the environments that the administrator provides, but can bring their own, and so the infrastructure can evolve with its users. But with all of these exciting advancements and things that Jupyter brings, the tech alone is not enough. So plenty of Jupyter hubs and communities are not successful and don't reach their potential. And this is because a lot of research has shown that as we have success in innovation, only about a quarter of that comes from the technological innovation, and much of that comes from the social innovation that we wrap around that. So what policies are we incorporating? How do we use our tools together? What people are involved? That sort of thing. So we really need to drive social and technological innovation forward together to enable our communities. So kind of getting at that, as we use JupyterHub and Jupyter within a broader ecosystem, what advancements have been made possible so far? Just looking strictly at a computing algorithm, we can really accelerate science. So this is an example of a sea surface temperature algorithm that I built for a Landsat. A lot of the tools that I use are across the bottom. A lot of the different tasks, search, download, unzip, a lot of these are manual before we're using the cloud. And then we're storing pretty much every intermediate data product. And what that meant is we were kind of storing 6 terabytes of, this was 6 terabytes of data, and it was a weeks to months long pipeline because of all of this, the manual pieces of this. Now fast forward 6-7 years, once I got out of my grad degree, this whole pipeline is orders of magnitude less processing time and has way less data storage. We can do all of this in an automated way in 1 minute, and it's all made possible because we have the tooling for speeding this up. We have a persistent platform that we can use. The data format is optimized for this pipeline, and data access is streamlined with Stack. And what all of these things do together, built on top of the JupyterHub, is reduce the time for iteration. So as we have new versions of data come out, we don't have to go download an entire another data set for that. We just, at the touch of a button, reproduce everything. Time to solution is faster, and impact is much greater. We can also teach open science skills in a semester for $1 to $2 per student. And that's incorporating the right guardrails and best practices that have been built over the last decade. So in this case, Fernando Perez runs a statistics course at Berkeley where over the course of the semester, they do an entire research project. They make it fully open on a Jupyter book, publish the main paper and notebooks, and make it fully reproducible with my binder. So this is a class for 50 to 2,000 students at this cost. And because of this work that we've done in terms of guardrails and all the tools surrounding it, we can do it for this cheaply. Another exciting advancement is with the right things in place, we can get an undergraduate up and running on entire NASA data store in an afternoon, which was never possible before shared Jupyter hubs and the community behind it. So Jack Logan is the undergraduate there in the right. He's an undergrad at Colorado School of Mines, and he works on its live glacier velocity data. And he was able to do this because the data is cloud ready, there's geospatial tooling to work on it, he had a persistent platform to join, and an open community that shared training that is accessible to him as a new user, and that's state of the art. So it's bringing beginners to the state of the art really quickly, and really getting that expert knowledge to beginners so that they aren't having to reinvent the wheel and replicate things. So those are some of the advancements. We've also conducted surveys for CryoCloud to understand what our users think and how they use the cloud. One thing that was really interesting for us is that 76% of our user community was less than 5 years out of their PhD. So it's really young. And especially, and this is, especially the case for federal agency, a lot of the decision making around policies and what's happening next for the computing that we use, all of those decisions are being made by people who really have not used the cloud much. And so a lot of the expertise is in younger populations, and we need to be incorporating them in decision-making to be making the right decisions around the cloud. Another thing that we found is with the right bumpers, we can operate for research purposes at much less than the price of the cost for a laptop per person. So daily cost is in gray here, and daily users is in red. And the gray is a combination between compute and data storage costs. And we calculated it out, and per active user, we're spending about less than $1 per day, $187 annual. And on average, our users are using 26 hours of compute per month. And over the course of 5 years, this is much less than the cost of a laptop. So it might make sense for researchers to actually be using, less expensive tablets and accessing the cloud than buying a similarly performative computer. We've also found that all of this requires expert engineers, user-level monitoring, and continuous training. So the first yellow line here highlights a place where we accidentally left an instance open, and so you can see we spent a lot of money leading up to when we found that and fixed it. This is a problem that obviously a lot of us can run into these bugs, right? But this is actually analogous to decisions that a lot of IT teams and institutions are purposefully making. They're leaving open instances for like 24/7 and spending a lot of money. So having cloud engineers be a part of this who are experts and building this infrastructure is really important so that you save on costs. User-level monitoring also is really important, right? You can see that our costs kind of went up at one point and then went back down. This was from increases in data storage because our users forgot that they needed to delete their data and started storing tons of data. So we allow our users to store 10 gigabytes of data. They can go above that. We didn't have restrictions on that at the beginning of implementing CryoCloud. And one of our users was starting to store 4 terabytes of data every day, and lots of other users were going beyond that. So once we manually realized that this was happening, because there wasn't any monitoring systems in place at that time, we emailed the user, they brought it down, and we've since created documentation that we send out regularly to our users to remind them to remove data they haven't used and to tell them how to do it properly so that they don't accidentally delete other users' data and know how to do it properly. So this keeps our costs down, and so that continuous training is really important because no one remembers that they're using the cloud. It's really invisible, so we default to what we do on our local computer, and it costs a lot of money. Another exciting thing that we've recently realized is, well, it's not exciting, also requires more training for our users, is that users are requesting a lot more compute than they need. So I'm going to break down this figure here. Each block is an aggregation of data for one day across the month of October 2024. The numbers are the number of users for that day. The top line is, all of this is looking at the ratio, the percentage of amount of data that or amount of compute that they're using versus the amount of compute that they've requested. So along the top is just a median percentage that users have used throughout the day. So on average, 21% of memory of what is requested is actually being used. So very low amount of what is requested is being used. But you may think, most users actually request the amount of data that is request the amount of compute that is the max amount that they're going to need for a notebook. And so we've computed that at the bottom, in the middle line there. So this looks at the median of the maximum that each user is using, and still our users are only using at most 50% of the memory that they've requested. And then along the bottom line, we're seeing what the #1 most efficient user has used, and max usage is between 50% and 98%. So even our best users are not always doing a great job. So this really goes to show that we need to train our users a lot more about how much compute they actually need, because in our surveys, they actually told us they think they need a lot more than we actually provide, and they're really not using it. Motivations for working in the cloud stay relatively stable over time. The main motivation that we've found both for new users who've been on for less than 6 months and people who've been on for more than 6 months is that they don't have to download data and don't want to store data. That's the main reason for switching to the cloud. In terms of what they show are their biggest challenges, the new users really worry about their skills and expertise in working in the cloud. But our longer term users show more worry around cloud, controlling cloud costs and streaming data from the cloud and not being able to do that. And so there's really a tension for our users between them being motivated around data and data access and not having that data and access in the cloud being readily available to them. So there's a huge tension there that needs to be solved, both at data standards levels and policy levels and things like that. We also asked a number of questions here. We've broken this out by the time that a user has used or been on the cloud again, with the light green being the longest amount of use. And while a lot of these progress kind of to the right as people become more familiar with the cloud, what's interesting is that the fact that the question of whether they want to compute all of their work in the cloud does not change. Users don't want to only use the cloud. A lot of our users, if they only need one small data set, they're staying on their local computer. And when they want to use big data, they're doing it on their cloud platform. So there's a lot of diversity in what our users want to use in terms of ecosystem of compute. We've also put together insights from the other JupyterHub administrators that we've worked with. And I'm only going to show the ongoing barriers for the users, but I also do have slides about what the barriers are for administrators. So if you want to ask me about that later, I can show you. So common major challenges for users, again, around accessing data. They still rely on download-based workflows. Programmatic authentication is problematic. There's legacy data formats that are in the cloud that prevent streaming, and a lack of best practices for accessing large and restricted data sets. And so things like data centers implement reCAPTCHA in accessing data. Something like that prevents all of their users from being able to even automate download. Like, we don't even talk about streaming. You can't automate downloads. You have to manually download into your local computer and then put it into the cloud. So data centers are a decade or two behind cloud computing for the most part, and we really need more advancements there. Users also have unpredictable and untenable costs when scaling up and limited support on managing or monitoring cloud spending. So at NASA, I had one user say they were planning for their next NASA mission, and they wanted to do all of their work in the cloud, which is what NASA was kind of like pitching at the time. And that would have cost 1/3 of their mission to be able to do that instead of putting it towards the instrument, and they just can't support that. So we need to have a way to more cost-effectively scale up. Users also have difficulty accessing JupyterHub and cloud storage due to limited permissions, bureaucratic hoops, restrictive policies, and uncertainty around how to get needed access. So Ellie over in the corner there is part of our CryoCloud team. She switched to Stanford and needed to get data access credentials moved between where she was before at Berkeley and at Stanford, and that took 3 months. And not just like 1 hour and a few emails, but like tens and tens of hours across 3 months to get that set up. So our users are having a lot of problems with authentication. They're also finding insufficient IT expertise, like I mentioned before. IT is choosing the wrong implementation and guardrails for JupyterHubs and accessing the cloud, and no institutional support for the research workflows that are required to do this. And then few beginner accessible on-ramps. So a lot of our users don't know how to use GitHub and won't ever do that. JupyterHubs are challenging, and again, best practices. So we really need to have beginner accessible training to bring people into the cloud, not just be writing our training for each other. I have a JupyterHub needs wish list. Some of the barriers that we've run into, definitely take a picture if you're interested. I will say that we love to use Jupyter Collaboration and Jupyter AI, but we've had frictions in being able to use those and implement them. a lot of file sharing things that we would like, and file syncing, cost monitoring button in JupyterHub, so we can train users to be able to see like what they're using and react to that. And then being able to have more portable compute and cheaper scaling solutions. So on that note, I'm going to talk about how we kind of overcome these barriers that we've kind of been going over. And at the end, build a roadmap to a thriving community. So as I mentioned before, social innovation is far more important. And so than the technology. So pairing computing with frictionless communication is one of the big steps that we can make that will facilitate community building. We use Slack because our users are really excited to use that. There are a number of other options here. This is an example of a Slack message that one of our users wrote, Sean Foley, when he was running an event. He found that GPUs were underperforming in comparison to what we were expecting on a JupyterHub. And so over the course of 4 hours, he got 31 responses, a lot of them from UV, who's sitting in the audience, who were working to solve this. Within 4 hours, there was a solution. It was implemented across our hub and the 109 other 2i2c hubs, and then pushed upstream to JupyterHub as a recommendation for them. And that was all in 4 hours, right? This isn't something that you can actually accomplish if you're using support tickets and the asynchronous kind of transactional system that ITs have, a lot of ITs have. So having this like synchronous, very casual way to communicate, you start getting new questions and you start being able to very rapidly respond to issues. And actually, if we look at how Slack and JupyterHub are used together, this shows our monthly users. After the events that we have in summertime, we have a big peak, and then things drop off a little. The collaboration and communication over Slack is maintained and stays very high, while on JupyterHub it goes down for the season and then comes back up the next year. So Slack is really important for maintaining collaboration and everything that we've used for troubleshooting and things like that. And what's really important as part of this Slack or communication space is that all the different kinds of the users, different users and engineers, cloud engineers, the tool developers are all in the same space so that they can answer questions. So it's not just users and one person on IT following this. And that really accelerates feedback and collaboration. Everyone can see where the problems are, and tool developers can see where they need to improve their tooling. This also creates a shared community resource model, so experts can do what they do best, and users don't have to become cloud engineers. And this really maximizes the impact of each research dollar. So this really creates an open source community without boundaries and empowers our community members to do what they do best. Now, as I said, we would have a model at the end for suggestions of what I think help contribute to a thriving community and not just a Slack. So to build a strong foundation for collaboration, kind of get to co-creation where we get this rapid feedback, we need a strong technical vision, a welcoming code of conduct, a shared and efficient communication space, and shared environment and computing space that's persistent for our users. We also need to invite beginners and experts from all parts of the tool chain and IT, not just the researchers or whatever that are users. We need to have training that resonates with beginners and documentation for beginners to contribute and develop. And last, to encourage co-creation, we want to share products early and often, make upstream open source contributions, encourage intellectual generosity and sharing, and have a commitment to open source and open collaboration. And so all of these kind of feed back on each other and are really important, but what I want you to notice is within this, we have JupyterBook potentially supporting documentation. We have our JupyterHub as a shared computing environment. So really at the core, the infrastructure that is supporting all of this is Jupyter. And so as we have this ecosystem that's kind of built, we have this social innovation that's built around that. Jupyter really is at the core of all this. So with this, as we have these interconnected systems, we need to work across these. Really facilitating interconnected communities is important, and Jupyter does that. So with that, thank you.